Hi students, if you haven't already, make sure that you print out the note sheet to go along with this screencast. This screencast is about comparing fractions and the four methods that we use. You've already heard a little bit about these in the illustrative mathematics videos that opened up this module. They were the beginning of this module, but I wanted to kind of go through these methods again. And make sure that we go through several examples and give you some details on this. So there's going to be four methods of comparing fractions, and the first method involves using 1/2 as a benchmark. And I really like this because it doesn't require a lot of work. The only drawback to this one is that it doesn't always work. And the reason will become apparent in a second. All right, so I have this diagram here just kind of as an aid as I'm explaining. And what this diagram does is show a lot of equivalent fractions. And so you see this pink bar going down the center, and this is showing 1/2. So we've got 0 on this end, 1 over here. So 1/2 is exactly 1/2 between 0 and 1. And we see that there's all sorts of names for 1/2. There's 2 fourths, 3 sixths, 4 eighths, 5 tenths, and so on. And what's important here is to notice, hey, we've got a lot of fractions that come before 1/2, a lot of fractions that come after. And the way that we can know whether they're going to fall before 1/2 or after is by looking at and comparing the numerator to the denominator. So if you're exactly half, then that means your numerator is exactly half of your denominator. So 2 doubled would be 4, and 3 doubled would be 6, 4 doubled would be 8. Notice that there's no fraction here because it would take 4.5 to be doubled to get 9. I mean, that number makes sense to us. It's just not a number we put on a number line. 5 doubled would be 10. So we can look at these two fractions here, and we can essentially say, hey, 5/9, it takes 4.5 to have exactly 1/2. So I know that this fraction here is greater than 1/2. 2/5, okay? So exactly 2.5 doubled would be 5, and I've only got 2 of the fifths. So I know this fraction is less than 1/2. So that means this fraction would fall between 0 and 1/2 on the number line. This fraction would fall between 1/2 and 1 on the number line. So that makes this fraction the bigger fraction. All right. Similarly, I can look at the next one and look at 3/5, which is right here on my number line, 3/8, which is right here. So again, these first two, you can clearly see on the number line where they're falling and know that 3/5 is going to be bigger than 3/8. But we want to compare the numerator to the denominator. So on this one, 3 is bigger than 1/2 because it takes 2.5 to be half of 5. So this one is greater than 1/2. It takes 4/8 to be 1/2, and we don't have 4. We only have 3, so that makes this one less than 1/2. So since this fraction is bigger than 1/2 and this one's less than 1/2, that has to be our bigger fraction. Finally, on this last one, these aren't shown on the number line, so we have to just use our reasoning. So if I look at 55 and I double that, that would be 110. So if it was 110 as my denominator, I'd have exactly half. My denominator is bigger than that. So what this is telling me is that I have less than half. Okay, so this fraction is less than 1/2. This fraction, I'm going to just talk about this slightly differently, go at it from the other angle, which is, let's see, half of 125 would be, what, about 62.5? Well, 68 is more than that. So this means this fraction is greater than 1/2. So that makes that the bigger fraction. Now up here at the top I said this doesn't always work. Well, here's a case where this wouldn't work. If I had, let's say, 6/9, and I was going to compare that to 7/8, I'd have a problem. Because if I try to use this idea of compare to 1/2, 5.5 is exactly half of 9, so this fraction is greater than 1/2. 7/8 is clearly more than 4/8, so this fraction is also greater than 1/2. So in this case, this strategy would not work. Okay, we're going to go on to the 3 other methods, which all of these methods very much depend on having the understanding of fractions that is presented in the Common Core. So that means that you need to remember the numerator of fraction tells you how many pieces you're counting, and the denominator of a fraction tells you the size of the pieces that you are counting. So our 3 other methods are common numerator. When you have common numerators, it means that you have the same number of pieces, but that the size of the pieces is different. There's the common denominator strategy, which we're most familiar with. And in this strategy, the size of the pieces is the same, but the number of pieces that you have is different. And then the missing pieces strategy, which I think is a really cool strategy. In this, neither the size nor the number of pieces is the same, but they're both missing the same number of pieces in terms of how close they are to being one whole. So let's look at some examples here. So these are common denominator examples. And when you are taking the exam that covers fractions, you're going to be answering these types of questions in essay format. And it's going to be critical that you use the terminology size of pieces and number of pieces. So there's no exact wording that's perfect, but you cannot you can't say something like the numerator of this one's bigger than the numerator of that one, because that's just not going to work. So what you could say is they are both 9ths. And now we're comparing the number of pieces, right? So they're both the same size of pieces. Here we have 8 of the pieces. Here we have 7 of the pieces. So they're both 9ths. Let's change that and. But 8 pieces is more than 7. Sorry about my terrible handwriting yet again. So in this example, essentially what we're saying is the size of the pieces is the same, but this first fraction has more pieces, right? And that would be the explanation that I'm looking for. The second problem doesn't have common denominators yet, but we can take care of that. So we look at the 7 and the 3, and the denominator that I can change them both to, that is the smallest, would be 21. And I would do that by multiplying the first fraction by 3 over 3, and the second fraction by 7 over 7. So that makes this first fraction 18 over 21. And it makes the second fraction 14 over 21. So as you were doing an explanation, you would need to say same size pieces, and then something like 18 pieces. Is more than 14 pieces. So that would make 6/7 greater than 2/3. All right, so now we're going to move on to the common numerator examples. So remember in this one, the number of pieces is the same, but the size of the pieces is different. So we're going to compare the size of the pieces. So number of pieces is the same. So we're going to compare size of pieces. And this we always kind of go back to the old pizza thing, okay? So I've got a pizza cut into 5 pieces, and I have the exact same size pizza cut into 7 pieces. If I'm really hungry, which pizza do I want to get a slice from? The one that was cut into 5 pieces or the one that was cut into 7 pieces? Think about it. This is less pieces, so that means there's more pizza per piece. So what I would write is 5ths are bigger than 7ths. So that makes that the bigger fraction. All right, next one down. Again, this one does not have common numerators right now, but we're going to first do that. So I've got a 6 and a 4, and I can turn both of those into 12s so that I have common numerators. And I do that by multiplying the first one by 2 over 2, and the second one by 3 over 3. So I end up with 12/18, and over here I have 12 over 21. So they both have 12 pieces. So I need to compare the size. Right? And again, I do the whole pizza strategy. So if I have a pizza cut into 18 pieces, and the other pizza is cut into 21 pieces, the one cut into 18 pieces is going to have the bigger size pieces. Okay, so I'm going to kind of try to shorthand this. 18ths, rather than write that out with letters, are bigger than the 21sts. So that makes 6/9 bigger than 4/7. All right, finally, what we're looking at is the missing pieces example. So they don't have the same size pieces. They don't have the same number of pieces. But what they do have in common is that the first one is missing 3 pieces. And the second one is missing 3 pieces. And by missing, I mean if 6/9 had 3 more pieces, it would be whole. And if 4/7 had 3 more pieces, it would be whole. So then what I do is I say, well, which is missing more? So these 3 pieces versus these 3 pieces. Which of these pieces is bigger? These are 7s. These are 9s. So these are bigger pieces. So if those are bigger pieces, then this pizza, if you're going to keep going with the pizza analogy, is missing more than the other pizza. And if it's missing more than the other pizza, then that makes this the bigger fraction.